Select the major product of the following series of reactions. So when we're approaching a problem like this, we want to look at what we're starting with, and then we want to take it sequentially through the steps that we are given. So we see that our starting material is an ester. And the first thing that we should recognize is what we're doing here in this first step. So we've got dibal H. So hopefully you remember what dibal is. So that is diisobutyl aluminum hydride. And we are doing this at a low temperature. So a hydride reagent, this is a reducing reagent. And what this is this is a selective reduction. So selective because what it's going to do is it's going to reduce the ester to the aldehyde rather than taking that ester and reducing it all the way down to the primary alcohol. So after this first step with the dibal, we should have taken that ester and reduced it to the aldehyde. And I am going to, as I'm drawing this, just to make sure we have room to put everything on here, I'm going to abbreviate that benzene ring as a phenyl. So we're going to put PH for phenyl. Say we are reducing this to the aldehyde. Okay? And then these next two steps, treating this with sodium hydroxide, following that up with aqueous acid and heat, these are steps for an aldol condensation reaction. So what's going to happen when we treat this aldehyde with sodium hydroxide is you're going to have an acid-base reaction. And it's not a very favorable acid-base reaction in terms of forming a large amount of product. You'll form a small amount of it's going to be an enolate product at equilibrium. So let's take a look at that. So you've got alpha hydrogens to your aldehyde. And because of resonance with the carbonyl, these are slightly acidic. And so we can form a little bit of the enolate by treating this aldehyde with your aqueous base. So this is going to remove a proton at the alpha carbon. And I'm going to draw the resonance form that puts these electrons onto the carbon. And that is resonance stabilized with the carbonyl, but I'm choosing to put them on the carbon so that we can clearly see that that alpha carbon becomes nucleophilic as a result of this deprotonation. So we're going to form some of the enolate, but mostly still have a lot of aldehyde in here. And that's important because we're going to have the enolate that we form react with the aldehyde that is still in there. So let's go ahead and draw that enolate. Okay, so we form a small amount of it, and what's going to happen is it's going to react. And once it reacts, then it's no longer in the equilibrium, so the equilibrium will shift and form a little bit more. And then that reacts, and the equilibrium shifts again, and that's kind of how this reaction proceeds. So I want this to add to another equivalent of the aldehyde. That's what's going on in your aldol condensation. So I'm going to go ahead and draw another equivalent of the aldehyde here. I'm going to draw it in a different color so we can keep track of the two equivalents that are coming together here in this reaction. So we've got a nucleophilic carbon and we've got an electrophilic carbon. So we're going to show these reacting with each other. And this is the key carbon-carbon bond forming step of this aldol reaction. So we are bringing together the alpha carbon of one carbonyl and the carbonyl carbon of the other. So this is going to form, so this is our new bond. So I'm going to go ahead and draw this aldehyde piece. And the alpha carbon is where I formed my new bond. And then I've still got this substituent kind of phenyl ring hanging off of there. So I'm going to angle this down so that I can highlight where the new bond was formed here. So here is that new bond. And then here is the carbonyl carbon right here. So it is going to have an oxygen with a negative charge now, and a bond to the CH2 and the phenyl. And if you want, you can draw the hydrogen on there. You don't have to because that would be understood to be there in a skeletal structure. All right, and so if you've got this aqueous base, you've definitely got some acid around too. So what we can do is we can assume that we're going to protonate that to get the alcohol. So we can draw some water and put the proton onto here. Okay, so now we're going to be drawing the aldol addition product. So I'm going to keep highlighting where that new bond is. And then you've got, now this is the alcohol, and you've still got that phenyl ring. So this would be the product of step 2. So this is the aldol addition product. And so what's going to happen to this aldol addition product if you add in aqueous acid and heat is you're going to protonate this so it becomes a good leaving group, and then you're going to have the elimination. So as you heat this, add the aqueous acid and heat this up, you're going to have the elimination to form the alkene. So I'm going to go ahead and draw the product with the alkene. So where that alcohol was, I'm going to say that that was eliminated, and we now have a double bond. We have a phenyl, and we have the aldehyde. So you want to try to recognize this from our options here. And this aldehyde, just to help you find it, this CHO group can also be abbreviated as CHO, which we often do when we don't have a lot of room to draw a structure. And then with that, if you think about that abbreviation, you can hopefully recognize that this structure D is the same. So I'm going to go ahead and highlight the pink and blue carbons so that you can more easily pick this out. All right, so we've got that phenyl ring, we've got the CH2, and then this carbon, the new bond formed, is a double bond if you've gone through and done the dehydration. And so, and then these atoms here, so that CHO is the abbreviation for your aldehyde, and then you have your phenyl ring. Okay, and so this final product with these acid and heat, we would call this the aldol condensation product.